Hello, my name is Dinesh Paspaleti, and in this video, I'll be going through the longest repeating substring problem, where I'll be explaining two approaches. One is the dynamic programming approach, and other one is the linear time approach. So, first of all, let's go through the problem statement. You were given a string of size n, which we denote it as a t of 1 comma n, which is a constant sized alphabet. So we want to find the longest substring of t appearing at least twice. So by going through this problem statement, we can say that is similar to the longest common substring problem, where the goal there is to find the longest substring that appears in the both the strings. But in this case, we have to find the longest substrings that appears at least twice within the same string. So the dynamic programming approach between these two are can be similar. Uh, so this problem can be easily solved in quadratic time using dynamic programming. As I mentioned, it is similar to the longest common substring problem. So let's denote t of I comma n, which means that the suffix of t starting at location I. So that is the denotation of t of I comma n mean. And also let us define another function called longest common extension, which we call it as LCE. So we define LCE of I comma j equal to the length of longest common prefix of t of I comma n and t of j comma n. So let's go through an example so we can get an idea of what LCE is doing. So suppose t of I comma n, which is the suffix starting at index I, this is Mississippi, and this is t of 3 comma n is a suffix starting at index 3, and t of 6 comma n is suffix starting at index 6. So if you want to find LCE of 3 comma 6, we will get the answer as 3, which is SSR. That is the longest common prefix of t of 3 comma n, t of 6 comma n. So this is what longest common extension mean, the LCE function mean. That's how we define the LCE. So to calculate these LCE values, so to find the problem solution of a problem, we can simply find the maximum of all the LCE possibilities, and we can return that. That is the answer for the longest repeating substring problem. So our next question is to how to compute these LCE values. So for fixed I comma j, we can simply compute LCE of I comma j in a time equal to LCE of I comma j plus 1. How we can simply match the characters one by one of t of I comma and t of j comma n until we find a mismatch, which is a brute force approach. But for this approach, in the worst case, it takes big O of n. So for computing all the LCE values, this may take around big of n cube time, which is not efficient. So we can come up with the dynamic programming approach, which is similar to the longest common substring problem. So while comparing to while comparing the two characters, if t of I and t of j are different, it means there is no common prefix between the suffixes. So we will take LCM of I comma j equal to 0 in that case. Suppose if t of I and t of j are the same, that means there is a common prefix of length at least one between the suffixes t of I comma n and t of j comma n. So in that case, we will take LCM of I comma j equal to 1 plus LCA of I plus 1 comma j plus 1. So using this recurrence, we can fill the dp table in a big of n square. So we can find the maximum values of maximum of all the LCA values in the table, and we can return that, which is the answer for our problem. So for this solution, it will take big of n square time. So still big of n square takes a lot of time, and can we do this in linear time? And yes, we have a solution for that too. So in this linear time approach, we implement two algorithms. One is a DC3 algorithm, and other one is a Casais algorithm. So before going through that, let's go through some basic terminologies like suffix array, and we can move to the algorithms next. So the basic brief overview of the linear time solution is we'll take all suffixes first and sort them in lexicographical order. And we'll define an array called suffix array. Suppose we denote it as SA of 1 comma n, which denotes the sorted order of suffixes. And specifically, SA of k equal to x means string t of x comma n is the kth smallest suffix in the lexicographical order. So let me explain this through an example. First, generate all suffixes of the string banana. So when we start from the first index, we'll get banana, and we start from the second index, anya, and anya. These are all the all possible suffixes of the string banana. And if we sort them in lexicographical order, we'll get this result: a, banana, nya. So now we create a suffix array based on the sorted order. So the first suffix in the array will be the a. So what is the index of that? A is 6. So we'll show s of a of 1 equal to 6. So s of a of 2 equal to 4 means the second smallest suffix in lexicographical order is fourth index of the suffix which starts at the fourth index of the substring of the given string. So ANA is the fourth smallest suffix in lexicographical order. ANA is the second smallest suffix in lexicographical order, and NAN is the third smallest suffix in lexicographical order. So finally, we define the suffix uh, array of the substring string banana is s of a equals 6 comma 4 comma 2 comma. This is a simple example of how we calculate the suffix array and we store the lexicographical order of that suffix of a given string. And next, once we get this suffix array, if we do that suffix array in lexicographical order in a linear time, and now the two suffixes that share the common prefix will be consecutive in this sorted order. So we can simply compute LCE of only those pairs of suffixes that appears consecutively and report the maximum value as the answer. So no need to calculate all the possible chances of pair. We just need to calculate only the adjacent pairs because the two suffixes that share the longest common prefix will be in lexicographical order. So they will be adjacent in the sorted array. So we compute LCE of S of AI and S of SA of I plus 1, I and I plus 1, which mean the adjacent one, and we report the maximum as the output. So if we do this LCP array calculation in a linear time and that suffix array, lexicographical suffix array in linear time, then yes, we can get a solution for our problem in linear time. So can we construct the suffix array in linear time? So yes, we can do that using the DC3 algorithm, which is called the difference cover 3 algorithm. Now let's go through that algorithm. So here we are defining a inverse suffix array. So we previously defined looked at how a suffix array is, and now we define inverse suffix array. Here we contain two arrays. Here R array is the rank array and L array is the leaf array. There are R suffixes that come before Ti in sorted order. So suppose these are the all possible suffixes of the given string, and for the string the rank is 6, which means it is the sixth smallest suffix in the lexicographical order. And for this AN the rank is 2. And suppose this leaf array stores the rank of each suffix, which means the first element in this leaf array contains the smallest suffix in the lexicographical order, which means the zeroth rank one. So, and the next one contains the 1th rank string. We store this index, which is 5 of the string, and the second element contains the second rank index, which is the 7, and third element contains the third ranked index, which is 3 itself. So that's how we store two arrays, R of I and L of R. So by using these, we can get the ranks and the index of the suffix going left and right. So the next is how we are sorting this in linear time, this suffix sorting. So there are three steps in the DC3 or skew. This is also called as a skew algorithm also. So basically, we have three steps in this process. The first step is to compute rank array R1, 2 for suffixes T of I, starting at I, which are not multiple of 3 recursively. So here we recursively compute a part of the answer which are not multiples of 3. This means 2 by third is computed recursively in the first step. What we're doing recursively is the 2 and 3, which is the we induce another rank array R3 for suffixes uh, T0, T3, T6, T9, so on, which are the multiples of 3. And we can do this, we can create this rank array using R1, 2, which we'll be going to discuss in the next slide. And once we define create these two arrays, rank arrays, R1 or 1, 2 and R3, uh, we can merge these two arrays and we can finally get a rank array R. By that we can get the suffix suffixes sorted in a lexicographical order. So let us assume for now the step 2 and step 3 can be done in linear time. So if these two can be linear time, in the step 1 we are computing it recursively as we are only considering the only 2 by third part of the elements. So in the first step we will be linear, it will be done in linear time, and next we are only considering the 2 by third. So only 2 by third n will be computed, and the next 2 by third into 2 by third of n will be computed, and so on. While considering the upper bound, we can get an output as 3n, which is linear time, which is big of n. So if we prove that step 2 and step 3 are possible to implement in linear time, then our algorithm works. We can implement in entire thing in the linear time. So let's see how we can implement step 2 and step 3 in linear time. For now, let's assume that we know the rank array R1, 2. So we know the rank array. So this contains suffixes which are sorted like T1, T2, T4, T5, which are not multiples of 3. And the multiples of 3, which is the R3 array, is undefined. We have to sort this T0, T3, T6, T9 in linear time. That is our second step. So we are doing it now. So suppose if we want to compare T0 and T3, uh, characters comparisons or sorry, uh, character comparisons are expensive. But after removing first character, we can obtain T of 1 and T4. Suppose T0, T3, we are comparing every character is really expensive. But we can convert this T0 and T3 like this. So this contains the characters like this. If you are able to compare these two characters, and this will nothing but the T1, and this is nothing but the T4. So instead of calculating the entire string, we can only compare the first characters, and the T1, T4 rank we already know that, which we can get from the R1, 2 rank array. So we'll convert this T0, T3 like this. If we pair T of 0, and rank of 1, which is the T1 suffix string, comes before pair of T of 3 and rank of T4 in lexicographical order, then we can do it in constant time without calculating the comparisons between every character. So This T0 and T3 can be compared using T1 and T4 in constant time. So, like that, yeah, you can see this T0 can be written as the first character and the rank of the T1, and the T3 is written as first character and the rank of T4. Like that, everything is converted into first character and their ranks. So, this is the R12 rank array, which is known, and based on this, we will compare in constant time using radix sort. We implement counting sort array by two iterations, which we can do it in big of n time. So in the big of n time, we can sort this R3, R0 rank array in big of n time. So now we got the R0 rank array, and this is the R12 rank array. And now we have to prove the step 3, which is the merging one, merging these two rank arrays in a linear time. So let's see, we can compare each from the this string T21, T22, T18, T20, and so on, and we can measure these like simply sorting, merging two sorted arrays. But this can be expensive in some cases. Suppose if we consider comparing T15 to T11. We apply the same trick as before for everything. We will only consider the first character and the rest as T16. This is first character and T12. Rest as the second string. But in the case of T16 and T12, we can't compare the like that. We can't compare the T12 and uh, we can't compare T16 and T12 either because they both belongs to different rank arrays where T12 is in R0 rank array and T16 is in the rank 1 comma 2 rank array. So we can only compare two strings which are in the same rank array. So here we still simplify it like T16 can be written as S T17 and T12 can be written as T13. So here T15 can finally written as A S T17 and T11 can be written as A T13. So here we have to compare two characters and other one we can get the rank. So simply three comparisons. So by using this we can do it in the constant time. So using standard merging method from MedSort, we can speed up comparisons using this rank R1 comma 2 as we done before. So by this we can implement the step 3 and step 2 in big of n time. But we cheated in step 1 where we mentioned that we know the rank array R1 which we computed recursively. We took it as we know the rank array. But we have to prove that we can also compute the rank array in linear time. So taking a subset of suffix is not an instance of the same problem as taking all the elements of the string. So for this, we need a single string t dash to recurse on, from which we can deduce a rank array r1 comma 2. So here we declare for this string t, we declare t box where we redefine the alphabets to triples of characters. We form triplets of the characters like BAN we form a box, AN will form a box, BAN form a box, and last $3 will form a box. So this is nothing but this is the T0. T0 suffix string starts with this BAN and T3 suffix string starts with ANA and T4 T6 suffix string starts with BAN. So these are nothing but the starting suffixes of suffix strings T0, T3 which are the multiples of 3. But we need uh, suffix strings which are not multiples of 3. So we declare T dash such that T1 to N box, these dollars to fill the triplets of the last character, and T2 of N box and the dollars. So From this, we can get the suffix strings which are not multiples of 3. So we can call suffix sorting recursively on T dash, and we can map the result to the R1 comma 2. So suppose let's take T string this, and if we consider T1, we will remove H and we'll consider from A to the last character. So by this we can see we can format triplets of size 3. We format triplets like this, and for T2 also we format triplets. We created a box for every 3 elements. So somehow we managed to reduce the comparison operations, but still it doesn't work because each recursive step cubes sigma by using triples. So we cannot use any linear time sorting anymore because having at most 2 by 3 n different triples, the it will be cube and cube in recursive steps, so it will be in exponential time. We cannot implement in the linear time. So before doing the recursion, we convert these triplets of characters into numbers by we sort all the occurring triples, replace them by the rank in sigma. So let me show the how does that work. So these are the occurring triples. So we remove the duplicated triples, and in this sorted triples, we sort these triples in lexicographical order and we assign some ranks. And finally, we create T double dash, which ANN contains the which for every triplet we'll mention the rank of that triplet. So instead of this, we can simply compare these rank, which really optimizes the number of comparisons. So this sorting this sort all occurring triplets in 3 rounds of count sorting. This can be implemented in 3 rounds of counting sort, which can be implemented in big O often. So so we can say that we proved that step 2, 3 and can be implemented in linear time, and this recursive step can also be implemented in linear time. So overall, the as I mentioned here, the time complexity is big of, and this is the recurrence equation of the DC3 algorithm. So that's how we create a suffix array in lexicographical order. And next, we have to find the LCP array. So we can run another linear algorithm called Casais algorithm to get the LCP array. Now let's go to this Casais algorithm. So in the Casais algorithm, the key idea is to compute LCP values in text order. So this is a rank array, like this is a suffix array which we'll get from the DC3 algorithm. These two arrays, R of I and L of I, which is the inverse suffix array. We'll get it from the DC3 algorithm. So here, first in the rank array, uh, yeah, first consider this suffix string. So let's find out this in the lexicographical order, and we find it in the sixth position. So let's compare it with the previous string of that, and we will manually compare each character. So B is same, A is same, N and N is same. So we get a 3. Uh, so we store that one in the LCP array. So when we are comparing the next time, we will store this information, which is BAN is same for these two strings, right? We store AN because while considering the next suffix string, the first character will be eliminated. So this AN will be same for the suffix strings which are in the lexicographical order. So when we're comparing these two strings, this AN part will be same. So we can simply skip the first two characters and we can start comparing from the third character. So here A and A is also same, and we skip to the next index, and B and N are not same. So we can simply output for this index as 3. So We got LCP value 3 in this case. So for the next case, we can again store the information of A and A by eliminating the first element. As we when we move to the next suffix element in the array, the first one will be eliminated. So we can store the information of NA. So NA will be the same for the next suffix string. So for the suffix string, when we go to the lexicographical order, it will be NA part will be same with the previous suffix string. So we can directly start comparing from the third index. So B and are not same. So we can simply output the LCP value for this indexes as 2. So by this we can reduce the number of comparisons. So dropping first character of adjacent suffixes might not lead to adjacent shorter suffixes, but LCP entry can only be longer. So that's how we can efficiently reduce the number of comparisons, and we calculate the LCP values, and we can also keep another value called maximum. So we can store the max value of these LCP values, and we can return that, which is the answer for our problem. This is a simple pseudocode how Kasai's algorithm work. So the dominant operations of the character comparisons separately count those with outcomes equal to and not equal to. So each equal to implies increment of L, but L is less than or equal to n, and decremented is less than or equal to n times. So overall, we can do this entire thing comparison operations using 2n number of comparisons, which is a linear time. So the time complexity for this Casas algorithm is big of n time. So here L is the length of induced common prefix. From this we can say from our analysis we can say that as we can implement into n comparisons, this Casas algorithm can be done in linear time, and we also proved DC3 algorithm can be done in linear time. And that's it. That's how we find the solution for the longest repeating substring problem and linear time. And yeah, thanks for watching.